The last thing we'll talk about is the idea that you can use some of the continuous distributions to approximate the discrete distributions. Let's say you have a random variable which follows a binomial distribution, right? It computes the probability of having a certain number of successes if the probability of success is, p. Well, we're going to see later that we can view x as a sum of independent and identically distributed random variables, right? So if we want to know what the probability of having a certain number of successes among n trials, we would look at basically the probability of success among one trial and add it up, because each of the trials is going to work the same way. Not clear yet why that should be the case, but this is something we'll talk about later. At any rate, your binomial distribution looks like a sum of Bernoulli trials, so binomials with n equals 1. We can use the central limit theorem, which we'll talk about later as well, and then we can conclude from the central limit theorem that x, which would be the number of successes, minus the mean number of successes, which would be n times p, if p is the probability of success, divided by the square root of n times the actual variance, that should follow, roughly speaking, a standard normal distribution. So if you have a lot of trials trying to compute the probability of a number of successes given the probability of success being p in a large number of trials, that's about the same as a normal distribution, where the mean would be the average number of successes and the variance would be the number of trials times the variance of the Bernoulli distribution, p times 1 minus p. In other words, if you want to compute probabilities in the binomial context, you might be able to use the normal distribution to do so. So if you have a large number of trials, the probability that you will get x successes or fewer than x is going to be, roughly speaking, the same as the probability of the normal distribution z, the standard normal, being smaller than x minus np plus 0.5 divided by the square root of n times p times 1 minus p. This is standard normal, and this is binomial. And the probability of x being greater, the probability of the number of successes being greater than or equal to some value x would be given by this probability. What we're really saying here is that if you have a binomial distribution, if your number of trials is large, there's a normal distribution that, roughly speaking, corresponds to this. And then you might use the normal distribution to compute the area under the binomial distribution curve, right? There's some closeness between the two. So if you're trying to compute, for instance, things related to 36 trials, and there being a probability of 50% of being successful, so perhaps flipping a coin 36 times. If you want to compute the probability that you should get 12 or fewer heads, you can use the tables and compute the probability that x is equal to 1, probability that x is equal to 0 as well, and 2 and 3 and 4 and so forth, right? So in the binomial context, could compute it this way, but the problem is that if n is equal to 36, in your textbook or in your tables, you don't usually get binomial probabilities. So instead, what we're saying is you'll compute the expected value of the number of successes, that is 36 trials times 0.5 probability of success, so there should be on average 18 successes. You'll compute the variance, n times p times 1 minus p, it gives you 9, and you can use the normal approximation to predict, if you want, that the probability that there should be 12 or fewer successes would be the same as the probability z, where z is going to be x minus the expected value divided by the square root of the variance here. A standardized normal smaller than 12, the value of interest, minus 18, this value here, the expectation, plus 0.5, that's a correction term given as in the formula, divided by 3, which when you compute it is about the same as minus 1.83. So you are interested, roughly speaking, computing this value. And that's something you can evaluate from the table. It's about 3.3%. If you were to compute it directly using R and the P binomial function, then you would get that the probability of 12 or fewer successes is about 3.26%, which is pretty close to the 3.3% given by the table. So we have three ways of computing binomial probabilities. You can use the exact formula. Probability of x successes, that would be flat out n choose x times p to the x times 1 minus p to the n minus x, if p is the probability of success. You can use a table. If your n is smaller than 15 and p probability of success is, roughly speaking, 10%, 20%, 30%, all the way up to 90%, then the table will give you the cumulative distribution function, and then you can compute the probability by rearranging the terms of the CDF. Or you can use the normal approximation. Right? This is a good rule to use if both NP and n times 1 minus p are greater than 5, and you can use a normal approximation, the formulas that are given there.